video we are going to discuss how to start from a truth table in Boolean logic and write a Boolean expression in Boolean algebra that has exactly the given truth table. So let's start by coming up with some truth table, and we are going to start with a truth table for a function f, which is on two Boolean variables, and we are going to write some truth table for f. And of course, since f is on two variables, the truth table has 4 rows. And I'm going just to fill this truth table with some values. Okay, now how do we get from this to some expression in Boolean algebra that has precisely this truth table? One standard way of doing it is noticing that we can fully represent any function by looking just where the ones are, right? So if we have here rows 0, 1, 2, and 3 in the truth table, if someone told you, oh, I have this function f, and the f becomes 1 in rows 1 and 3, and only there, then anyone could reconstruct the truth table, right? You just have to put ones at rows 1 and 3 and fill the rest with zeros, right? Because a Boolean function can only have 2 values. So knowing where the ones are is enough to fully describe the function. So we could write f conceptually like this. F is a function on x and y, which is 1 on rows 1 and 3, right? That's one way of describing f, but that's not in Boolean algebra, of course, right? It's just an idea which we are developing. Now, you could try to get closer to Boolean algebra by saying, okay, f of x, y is row 1 or row 3, right? How does that make any sense? Well, suppose that this is something that becomes 1 if and only if I am on row 1, that is, if the values of x and y put me on row 1. That is, if x is 0 and y is 1. And this is some expression in Boolean algebra that has the same property for row 3, right? This is some expression that becomes 1 if and only if I'm on row 3. That is, if x is 1 and y is 1. So, that's how we are trying to encode f. We are encoding those rows separately, and then we can combine them with an OR, right? Because if f is 1, it must either be in row 1 or in row 3. But what could go here and here? What expressions in Boolean algebra can I write which are 1 if and only if I am on these rows? Well, this turns out not to be very difficult, right? Because here I am explicitly saying if I'm on row 1, it must be the case that x is 0 and y is 1. So I just have to say that x is 0 and y is 1. Right? So that's one way of encoding it. X is 0 and I could write AND as in logic, but well, the product of Boolean algebra fulfills exactly this role, right? If it combines 2 Boolean values the same way as an AND would, right? If I get the product of 2 Boolean values, the product is going to be true if and only both the terms in the product are true. So I could write it like this. Row 1 can be encoded as x equals 0 and y equals 0. And row 3 can be encoded as oh, actually, y equals 1. And row 3 can be encoded as x equals 1 and y equals 1. So we're getting closer and closer to Boolean algebra, but there is still this equal sign here. Well, again, we need to write some expression in Boolean algebra which is true if and only if x is 0. Well, that's just not x, right? So I can encode this as not x and can encode this as y, right? Because y, the variable y in Boolean algebra is true if and only if y is 1. That's, I hope, obvious. So this encodes row 1 fully. And here we can encode row 3 likewise as the product between x and y. And this product is going to be true if and only if x is 1 and y is 1, which represents row 3. Now, if we combine those two with a Boolean addition, that has the same effect as an OR, right? This whole thing here is going to be true if and only if this is true or this is true. Otherwise, it's going to be false. So we managed to write an expression that's all there is in Boolean algebra now. The expression is complete. So f of xy is equal to not x times y plus x times y. This expression here has exactly this truth table, right? Because it can only be true if this is true or this is true. And this is true if and only if I'm in row 1. This is true if and only if I'm in row 3. And, well, that's exactly what function f says, right? So, this way of going from a truth table to an expression in Boolean algebra is called DNF, which stands for disjunctive normal form. Disjunctive here means disjunction, which is or. Disjunction means or, an alternative between two possibilities. If either or both are true, the whole thing is true, otherwise it's false. That's a disjunction. So this is written as an OR of all the rows. And normal form means standard form. It's a standard way of writing a truth table as a Boolean expression. The standard way based on taking ones, making an OR of them, and each row, each one is represented as a product of all the variables in the function. Okay, to make the concept clearer, we are next going to do another example.